Hello. Yes, Nilesh, you have raised a hand. Do you want to ask something? Okay. So I think it's already 7:10. Yeah, Nilesh, ask. What? I could not hear you properly. Maybe you can type. That will help me understand your query. Okay. So it's already 7:10, and I think we should start this session. So okay, nothing. Okay, fine. So it's already 7:10. So I think we should start this session now. So let me share my screen. So yeah, I hope you guys are seeing my screen and my voice is clearly audible to you. Are you audible? Okay, I assume that everybody can hear me and everybody is present in this session. Okay, so let's start. Let's not waste our time because it's already 7:10. I have waited so long for others to join. I want that people should come join early so that the sessions are not missed for someone who joined late. Okay, so let's start then. Okay. Uh, Good evening once again. Let's welcome you all to this live session on non-conventional energy resources. This course is taken up by Professor Pratap Haridas. He is a professor in Department of Metallurgical and Material Sciences in IIT Madras. I am Rohit, your pure scholar in IIT Bombay. I will be taking this interactive session. So these sessions have been planned so as to build interactive component between the students of NPTEL and NPTEL itself, the course, so that you can ask your questions, you can raise your doubts, we can discuss the concepts, we can clear the queries. Okay, that's how these sessions have been planned. So what I have done for this session is that I will discuss the non-graded assignments first. So we will have a good concept grabbing session and you could ask your queries also. And later times we will shift to graded assignment questions. So these graded assignment questions are from previous run of this courses. So try to think logically, try to get into the questions and try to see how these questions can be solved. What are the concepts that are underlying within these sessions? So I think it will be helpful for you guys to grab the concept that has been discussed in weekly lecture slides 6, week 6 of the NPTEL course. So let's start. Okay. The question one is basically from non-graded assignment. It basically asks about the Stokely Squeezer limit suggests that a single junction solar cell has an efficiency that can reach 100%. So let me take a pen here. So it's saying that a single junction solar cell, let's assume this is solar cell. Okay. And sun is overhead. Overhead, you all guys know, just at the noon, when the sun rays are actually perpendicular to the solar cell. So that is called overhead. It's generally at the noon, assumed to be generally at the noon, 12 p.m. Okay. So the Stokely squeezer limit. This is the main concept here. Stokely squeezer limit. So if you know the Stokely squeezer limit, so we'll discuss more about this Stokely squeezer limit in upcoming slides. So as for now, we'll discuss this question only. The Stokely squeezer limit suggests that a single junction solar cell has an efficiency of 100% of the sun is overhead. So basically, this is the first statement. Okay, if you have gone through the slides taught by Professor Pratap, you would have easily figure out that this is a type of false statement. Okay, so now the main question that is to be discussed here is Shockley Quasar limit. Okay. Another thing is that key whether it is talking about single junction solar cell. So what happens if we take multi junction solar cell? Okay, so solar cell generally single junction solar cells are very uncommon. We don't have single junction solar cell. Solar cells are always in multiple junction. Many arrays are getting built up, then they converted to modules, cells, arrays, modules. So that's how a solar cell is actually designed and built. So I think if anybody wants to have a question here, if he didn't understand the underlying concept or anything, so let's learn the Shockley Quasar limit itself. What does these limits actually tell us about? So before that, let me see if anybody wants to join because many people join late in the session. Okay, so nobody wants to join. Also, you guys can actually ask your question in the in call messages also. Like you can type it here. Okay, so I can read your messages if everything is going fine. Okay, let's discuss about this Shockley Quasar limit. So basically, this limit it defines the efficiency of a solar cell, maximum efficiency that can be reached by a solar cell. So whatever we can assume that the maximum theoretical efficiency of a solar cell can be 100%. Like all of the sunlight can be converted to just give me a minute. Somebody's calling. Okay. Just give me a minute. I will be back in a while. Uh, I will be back in a while. So please read these slides and try to understand what these slides say. Okay, then I will come and discuss. Just give me 5 minutes. Okay, so welcome you again, guys. So, have you gone through the slides? Any queries? No queries? Okay, so let's discuss then. I think, yeah. Hmm. So, what is Softly Quisser limit? What does someone join? So, guys, try to join at time so that will help me plan this session accordingly, and it will also help you grab the concepts from the beginning. Okay. Okay, so what is Shockley Quasar limit? So Shockley Quasar limit basically tells about the maximum theoretical efficiency of a solar cell using a single PN junction. Uh, Focus on this single PN junction. It is not talking about multiple PN junction. And what is it? It's the maximum theoretical efficiency of a solar cell. So what can be the maximum efficiency of a solar cell? It is basically defined by the Shockley Quasar limit to collect power from the cell where the only loss mechanism is radiative combination in the solar cell. So only loss is actually considered as radiative losses. Okay. Then whatever power we can get from a solar cell is basically maximum theoretical efficiency of a solar cell. So you know that key if there is a cell and some sunlight is striking down, so if it is not normal to the solar cells, then there will be some losses. If the solar cell has a glass of transmittivity something, then there will be some transmittivity losses, absorptivity losses, similar type of losses. Okay, so based on that the maximum theoretical efficiency is defined for a single p-n junction cell, and actually it was calculated first by the William Shockley and Hans Joachim Quisser at Shockley Semiconductor in 1961, and the maximum efficiency they got was around 30% at 1.1 ev. What is 1.1 ev? It's basically a band gap between the semiconductor. Okay, I am sure that you guys must have gone through the previous live session and previous weekly lectures, so you have a clear idea of what a band gap is. The Shockley Quasar limit only applies to conventional solar cell with a single p-n junction. And see, focus on this third point. It only applies to conventional solar cell with single p-n junction. Okay, not only on conventional. What are conventional solar cell? Silicon based cell and with single p-n junction. Okay, not on perovskite based solar cell. Okay, the modern solar cell which we are coming with multiple layers and multiple. Okay, the solar cell with multiple layers can easily outperform this limit. So this is another thing. So is there any question on this? Read these 3 points carefully and try to think if there are any queries you want to ask. No queries? Okay. So let me move to the next slide. So here are some trick question for you guys. So can solar thermal system outperform this limit? So what are solar thermal system and how they are different from solar PV? So solar PV is like a device which gets sunlight and directly converts to electricity. Okay, sunlight. But what happens in case of solar thermal system? There is a device, it gets sunlight and it converts it into heat. So this is how the difference is. Okay, and basically it is converting sunlight directly to heat. So generally the efficiency of solar thermal system are quite higher than solar PV cells. There are no concept of band gap here. There is a concept of concentrating ratios and many different things which we'll discuss in later slides, later lectures. So yeah, definitely, solar thermal system can outperform this limit. The answer is definitely yes. What is the limit of multi-junction solar cell with infinite layers in normal sunlight? So it's 68.7. Okay, and the same with concentrated sunlight, it's 86.8. Okay, so you guys can note down these values. These can be asked in the final exams of the NPTEL also. Okay. So there can be question: what is the limit for multi-junction solar cell with infinite layers in concentrated sunlight? So yeah, this question can be what can be what is the limit for multi-junction solar cell with infinite layer in normal sunlight is higher than concentrated sunlight. Comment on that. Okay, so these type of question can be asked. Okay, so be clear on this. And one more trick question I wanted to ask, like what is the maximum efficiency achieved till date with solar PV? So many of you might not have some knowledge on this, but in lab generally we with experiments 47.1% efficiency has been achieved, but in general the efficiency varies between 17 to 24%. Okay, in general efficiency is this only, very poor efficiency, but yeah, this is the efficiency of solar PV at current rate. But there are some new materials being discovered like perovskite based cell. They have cracked the efficiency much higher, but yeah, they are costly and the material is not easily available. So yeah, I have tried to show a graph also, like how this softly quasar limit actually varies with band gap. So this is the efficiency chart, efficiency axis. This is the band gap axis. You see that key for single maximum reachable efficiency for conventional solar cell is 33.7, like here, at a band gap of something 1.1 or something. Okay, and this is the maximum efficiency. As you go higher with higher band gap, the efficiency drops. Similarly, with as you go lower, the efficiency drops. Okay, so this chart is pretty important. So you can see this chart. I want you guys to focus on this chart for 2 or 3 minutes. Okay, so let me see if anybody wants to join. Okay, nobody wants to join. Okay, so recording is going fine. Yeah. Okay, so I leave you guys with this chart for 2 to 3 minutes. Focus on this chart and try to find anything important or something interesting in this chart. Okay. Okay. So any queries? Anything you want to ask? No queries? Seems you guys have actually understood the concept better. Okay. If there are any queries, you can write it in this chat box. Okay. Okay. Let's move to the next question then. Next question is the maximum power point of a solar cell occurs at open circuit voltage. So this is basically a false statement. Why false? We'll see up in later slides. Okay, so this is a false statement. So let's learn about the open circuit. The main thing it is asking about maximum power point and the open circuit voltage. So let's learn about these concepts. So open circuit voltage is the difference of electrical potential between two terminals of an electronic device when disconnected from any circuit. Focus on this circuit. It's a closed circuit voltage. Why close? Let's see this. Okay, so whenever there will be electron traveling from this, so current will be traveling from in this direction. It will go through a load. It will come back to negative terminal. So it is a closed circuit. But what happens here? The current will go here. So this is breakage. So no there. So whatever the voltage we measure between two terminals is the maximum voltage that can be obtained from this power source. Okay, so this is the open circuit voltage. It is the difference of electrical potential between two terminals when disconnected from any circuit. Assume some losses between these with these wire, but these losses will be minimum because the distance is not so much. So yeah, no external load connected. So this is open circuit voltage. And why it is important? So we will discuss it in MPPT part. In later slides, you will see with IV characteristic curve. I will try to explain why open circuit voltage is important, short circuit current is important. Okay, in short circuit current, we don't connect any load. Okay, we just sort it out. So whatever the current flowing between these two junctions is actually okay. So yeah, I will leave you guys with 2 to 3 minutes on this topic, open circuit voltage and discussion actually. So yeah, I want you guys to see these two graphs, and if there are any queries, you can post it in call messages. So yeah. Okay, so no queries. Let me see if you guys have posted any queries. No queries. Okay, so yeah, let's just see. Yeah, everything is going fine. Okay, so next question is again this is about maximum power point. The maximum power point of a solar cell vary from manufacturer to manufacturer. Okay. So again, this maximum power point thing came down. So yeah, we'll discuss about this maximum power point thing. And yeah, it varies from manufacturer to manufacturer. Why it varies? So we'll see. There are various things that has that differs from like operational characteristics, the solar cell, everything. So yeah. So yeah, it's a true statement. Uh, and let's see why it's a true statement. So yeah, the maximum power point is what is the maximum power point first? Let's discuss this maximum power point thing. So this is the main thing up to onto which the solar cell is actually tested. The characteristic of a solar cell is very much defined by the maximum power point that can be obtained, and it is basically obtained from a IV curve, IV characteristic curve. Okay, so the maximum power point is the point on the current voltage curve, IV curve, current I for current, V for voltage of a solar module under illumination. What is illumination? So we illuminate it with light. Generally, it is 1000 watt per meter square. So standard is 1000 watt per meter square, but it is not fixed. So many manufacturers use it 1000, some use it 1200, 1100, 850, 800 also, 900 also. So this maximum power point can vary. But they write it on the solar cell itself. Like this has been tested for a maximum power point with illumination of this much watt per meter square. Okay, where the product of current and voltage is maximum. Somebody wants to join. Let me see. Yeah. Okay. So okay. So point on the current voltage curve under illumination where the product of current and voltage is maximum. So we will see. Okay, where the product of current and voltage is maximum. I will show you in the graph itself. The point at which and it is also the point at which most possible current is drawn from the solar cell. That will also that is also shown in the graph itself. I will show everything on the graph. And one more thing that you need to focus is that ki maximum power point changes non-linearly with environmental conditions. It doesn't change linearly. So changes that doesn't mean that ki if you increase the solar cell by let's say by 1000 watt per meter square, you are getting a x uh, amount of power. Okay, x kilowatt you say, and you double it 2000. Okay, so you will obtain 2x amount of power. You will say like here the illumination is doubled, so power generator will no. It doesn't vary linearly. It varies non-linearly with environmental conditions like solar irradiance, temperature, degradation level, and load profile. Okay, so now I am sure that key now you can easily answer this question like maximum power point of a solar cell vary from manufacturer to manufacturer. Yeah, it's a true statement. Why? These are the things that vary with manufacturer to manufacturer, load profile, inverse solar radiance, and many other things like how they make these solar cells, what is the level of testing. So yeah, that's why these things actually vary. Now try to focus on this graph. This is the main graph of a solar cell. The heart of the solar cell is in this graph. Okay, so this is case of ideal. This is kind of ideal case. Okay, this is the short circuit current ISC. So in the question 2 I have shown you what is short circuit current. So I am sure that you guys must have understood what is short circuit current, open circuit voltage, everything. And this is open circuit voltage. Okay, let me show you. This is open circuit voltage. So what is open circuit voltage? It is the maximum voltage that can be obtained between two junctions of any electronic devices. And short circuit current is the maximum current that can be obtained from a
two junctions of the electronic device or something. So when can you obtain a short circuit current? When you short the two junction points, na. And when can you obtain open circuit voltage? So you don't connect any load. So you that's why it is called open circuit voltage and short circuit current. So this is ideal case. X getting maximum power point, IMP into VMP, I maximum power point, V maximum power point, and okay, this is the actual graph, power graph. So this is basically for a current graph, how current varies from uh, right, and this is how power varies. Okay, so this is not ideal. I was okay. This is basically current graph, how current varies, and this is how power is calculated by multiplying V into I. You know, power equal to V into I. Clean. Hmm. Okay, so yeah. So if you see the power curve, the maximum power is occurring at this is the maximum power point. Okay, so whatever is the current at this point and whatever is the voltage at this point is multiplied IMP, I maximum power point and VA maximum power point. So that's how we obtain this maximum power point. So now you have got a fair idea about how this maximum power point is obtained. So this is the maximum power. Okay, that can be obtained from this solar cell. So I will leave you guys with this graph for let me erase and this also. I will leave you guys with this graph for 2-3 minutes, so you guys can actually focus and think about the concepts. If there are anything you want to interact regarding this, you can ask me anytime. Okay, so no queries. Let me see if you have posted any queries. Nothing. Okay. So let's move to the next question then. So this let me take a laser pointer. It's saying that during reverse bias, the N side of the PN junction alone is affected by the applied potential. So it's talking about reverse bias. What is a reverse bias? In reverse bias, the P junction is connected with negative side of the terminal and N junction is connected with positive side of the terminal. Okay. So let me show you also. So this is basically a false statement. The N side of the PN junction alone is not affected. Both the sides are affected. Okay. So this is basically a false statement. And let's see how it's a false statement. Pretty interesting to know. I think. Yeah, I put the. Okay, so what is a reverse bias basically? So reverse bias applied to a PN junction diode raises the potential barrier because p-type material is connected to negative terminal and it pulls the hole away from the junction. Okay, p-type connected to negative terminal, so what it will do, it will pull the hole away from the junction. Oh, let's say if this is the junction, so it will pull the hole away. Okay, similarly the n-type is connected to positive terminal and it pulls the electron, so it is pushing the electron and it is pushing the holes. Let's see here. So this is P N, beta is connected to negative electron and I is connected to positive electron. What it is doing? It is pushing the hose. Sorry, pulling the hose. And similarly, this is pulling the electrons because it is positive. So what it will do? It will pull the electrons. So both the sides, not a n side only. Like this is not the n side only. Both the side P and n side both are affected in reverse bias. Okay. So try to read these two slides and read the question. So in during reverse bias, it talking about only n side is affected. So no, you can see both the sides are equally affected. Okay, only n side is affected. Then this must be this only. This would be all holes, but this is not hole. This is all electrons and this is holes. So both sides are actually affected. Okay. So any queries? Let me raise. So you guys can focus on it clearly. Read this. Yeah. This also. Okay, so I am sure that this question can be easily understood by you guys. Okay, so if there are no queries, let me see if there are any questions you guys have asked. No questions. Okay, so let's move to the last question of the non-graded part of the assignment. So charge density as a function of position is constant across p-n junction. Okay. So based on different conditions, this can be a true also, this can be false also. Okay. Let's talking about charge density. What are charges? Plus and minus. Okay. So as a function of position for for reverse bias, the charge density can be constant. But for unbalanced bias type of thing, okay, the charge density cannot be can be this statement can be false also. So basically p-n junction has both positive and negative charge. Okay, so when you see a p-n junction, let's say this has positive charge, this is negative charge, and this positive and negative charge are both equal in depletion layer. So maybe this is a depletion layer and this thing is p-n junction. So yeah, these are both equal in depletion layer, and it is also assumed that there are no free carriers in the depletion region. No free carriers, only charges. So this statement can be true also. This charge density as a function of position is constant. Okay, as you move to different position, the charge density will remain constant. So if you apply a bias to it, so maybe that this is more, this is less. So yeah, there can be a time that the charge density can vary also. So both true and false both are correct in this case. Otherwise, in general, you can assume charge density as a function of position is constant across a p junction. It's a true statement. Okay. So these are graded part of the assignment. So what I will do, I will give you guys a break of 5 minutes so you can go through. So this basically this is not a break. You guys can go through this from question one. Those who have joined late also from question one to question five, which is graded part. So basically, you guys can recall the concepts, and if you guys have any queries, you can post it in the chat box. Otherwise, you can unmute your mic and you can ask me also. So there is no issue. You can unmute your mic and ask questions also. So basically, most of you guys have not gone through the weekly lectures, so I've tried to cover the important concepts discussed in the weekly lecture. So you guys can have a fair idea what a solar cell is, how it works, how the different things related to solar cells, different terms, technological terms, technical terms. Okay, so is it fine? Okay, so focus on these concepts and try to ask questions. Okay, so yeah, no questions, nothing. I suggest you guys should ask questions, should participate more, so that will help you guys to actually grab the concepts at a much clear level. Okay, so yeah, let's go ahead. So, after this, the graded assignment questions are basically straightforward, pretty straightforward type of question. So we don't need to discuss much on these concepts. The non-graded part has good. Most of things have been discussed in the non-graded part itself. So wherever there is some concepts, application concepts, so we'll discuss it. Okay. So let me take a laser pointer here. So this question asks both Fermi energy and band structure are flat when traversing across a semiconductor p-n junction. Okay. So this is a false concept, false statement. Okay, so they are not flat. They vary when you transverse across a semiconductor p-n junction. Why they vary? Because electron hole pairs are there. So these things actually vary. The variation is actually this is the variation which helps in generating these different concepts of solar cell to work. Put these different concepts to work. And can you recall the Fermi energy? So basically, Fermi energy level is the energy level occupied by an electron orbital at a temperature of 0 Kelvin. So if we put the temperature to 0 Kelvin, and this is the band, and this is the valence and conduction. It's very valence band, conduction band. So in between at 0 Kelvin, there will be some level at which these electrons will actually occupy. So this is the level which is Fermi level, and the energy maximum energy point, this is called the maximum energy point up to which electron could reach at zero temperature. So this is the Fermi energy. Okay, so this much energy is actually retained by the electron even at 0 Kelvin. So okay, so I think the concepts are pretty similar type and pretty conceptual type. So if you have any query, you can ask. I will wait for 2-3 minutes for your queries. Otherwise, I will move to next slide. No queries? Anyone? So I think we should move to the next question. So this question discusses ask about what are the advantages of having an amorphous silicon. You know, amorphous and crystalline. In crystalline, everything is arranged in order. Amorphous haphazard type of thing. So what are the advantages of having an amorphous silicon over the single and polycrystalline sample? So yeah, it is more flexible to keep on a substrate or contour. Yeah, it is more flexible. Why it is more flexible? Because they are not arranged in a particular manner. You can flex them. Okay, you can bend them. Okay, to give a substrate or contour. It possesses more dangling bonds and thus more number of different. No, it doesn't have more number of different. It is more effective in capturing solar radiation. No, polycrystallines are actually more effective in capturing solar radiation, and it is less expensive. Yeah, obviously, because for converting amorphous to silicon, then glass transition temperature, everything you have to perform different treatment processes to convert amorphous to silicon. So that takes quite expensive process, takes time and everything. So yeah, these A and D are the correct one. So go over this question, and if you have any queries, you can ask it down. Somebody wants to join now. Om, your mic is on. Om, can you hear me? Ah, okay. So go through this question. The correct answer is A and D. Okay. Uh, is there someone who want to ask something? Okay, Om, we are discussing the non-graded part of the assignment of weekly lecture 6. Plus, we are discussing graded part of the assignment of previous run of this course for weekly lecture 6. Okay? Okay. So, the correct answer is A and D for this question. And I will leave you guys for 2-3 minutes to see this question to discuss more if you want to discuss something on this question. Okay. Okay, so if there are no questions, I think chat box. Option B is also correct. Wait, sir, what is your opinion? So let me show. No, there are no more number of defects in amorphous silicon over the polycrystalline sample. Okay, so option B is not correct here. Option A and D are correct. Why? Because in amorphous silicon, the particles are not arranged as such in crystalline silicon sample. So whatever is a defect is actually normalized over the area, so there are no more number of defects as such in crystalline sample. Also in crystalline samples there can be shearing defect and many other type of defects which can be present in the crystalline samples. So these are actually amorphous silicons have this actually kind of benefit over this. Okay, so no queries, no any other queries. So let's move to the next question. So next question is solar cell. It basically you have to match section A, which is solar cell component, and with section B, which is ideal resistance. It's basically more sort of you have to remember these things, and if you have gone through the slides, you can really get the answer. Okay. So new solar cell, aged solar cell. These two type of solar cells. So be sure that key aged solar cell will have some different characteristics. So quite reverse to the new type of solar cell. Why? Because with the aging phenomena, the different resistance and different other thing behaves in somewhat a different manner. Okay. So for new solar cell, the shunt resistor, that is RSH, is basically high. Okay, because it's a new, the resistance is whatever we put it as a resistance, it will be high. Okay, and series resistor will be low. Okay, so this is basically a shunt resistance. This will be series resistance. So in case of new type of solar cell, this will be high. The shunt resistance will be high and series resistance will be low. There will be very less. You cannot hear me, Om. Can you hear me now? Am I audible? So okay. So yeah. So we were discussing shunt resistance and series resistance here. Okay. So what happens in new solar cell? The shunt resistance is actually high and series resistance is actually low. But as the aging continues, aged solar cell, the shunt resistance become kind of low and series resistance become high. Okay. So let me give to understand this concept better. Let me give an example also. So you guys can. I will take example for electronics, not from solar, so you guys can understand it better. So let's see. This is shunt resistance. Shunt resistance is basically parallel resistance. This is yeah. Let's say this is 1 1. This is also 1 1. No, let's say this is 2. Okay, so that this is high in initial case. So if this is 2, 2. So what is the formula for center resistance? 1 by 2 plus 1 by 2, and this whole thing is basically 1 ohm. So let me make it 4, not 4, 0.5, 0.5. So I think this is not getting set up. So it's basically difficult to put a value here for different types of resistance. It's series, huh? Okay. So what we do here, we have to make it, let's say, S1. So yeah, maybe other 2, this is 2, 4. Ah, okay. So this is working. Let's say make it 1, 1. Okay. The shunt resistance. So what is the formula for shunt resistance? Overall equivalent resistance, REQ. 1 into 1 by 1 plus 1. Okay. So basically it is 1. And series we have a single resistance. So we have 1 ohm. So what happens with the passing of time, these resistance actually get more because they degrade in value. So the resistance value get increased with aging. So what happens? Whatever aging takes place, this value will become distributed to two different lines. So the overall resistance will be much lower than series. Okay. So that's why in new solar cell the shunt resistance is high, the series resistance is low. In aged solar cell the shunt resistor is actually low and series resistance is high. So somebody wants to join. No sound. Uh, not sure why I'm not audible. I'm hello. Yeah, Om, can you hear me? Am I audible? Okay, so yeah, if there are some microphone issues, what you can do, you can try to disconnect your microphone and connect it again. Otherwise, you can leave the meeting and join again. So these are generally online meetings. So these microphone camera things actually happens a lot. So don't worry, it will not be a problem for you. I will upload these. These whole session is getting recorded, and I will upload this session on YouTube also. So when you go to problem solving session link in NPTEL portal, you will find these videos. Okay, so you can access from there also. So that's not a issue. Okay. So mm-hmm. when you have submitted the assignment after some days, like after 1 week, the marks are actually shown on the portal itself. So you can go to that week, that assignment, the marks will be shown there. On the on the Swayam portal, go to NPTEL course, go to non-conventional energy resources. There, the click on the week on which onto which you want to see the assignment. Okay, so you will be able to see the marks. Okay, that's not issue. Any other thing? Okay, okay, no problem. So let's move to the next thing, that is fill factor. So basically, fill factor. We will later discuss the formula. First, we will know what is the significance of fill factor actually. Okay, so fill factor is basically very important parameter that determines the power conversion efficiency of an solar cell. So it can be uh, assumed to be a power conversion efficiency of a solar cell. Okay, so there can be several factors that can influence the fill factor. But basically, what a fill factor is. So in the previous graph, I have shown you uh, the maximum power point, the current at maximum power point, the voltage at maximum power point, the open circuit voltage and short circuit current. Okay, so you have seen this graph, huh? There. So this is maximum power point. This is current, this is voltage. At some point there will be ISC, short circuit current, and this will be open circuit voltage, OCV. So this is IMPT and this is VMPT. Current at maximum power point, voltage at maximum power point. So fill factor is basically the ratio of current at maximum power point multiplication by voltage at maximum power point, that gives the power, maximum power, by theoretical maximum power that can be obtained from a solar cell, that is VOC multiplied by short circuit current. So this is correct. Fill factor, this formula is correct. And you see the option D. Option D is basically inverse of this formula. So this option is also correct. DD. So now you have got a fair idea what a fill factor is. So basically, fill factor determines the power conversion efficiency of an organic solar cell. So whenever we have to determine the efficiency of a solar cell, its fill factor is very important parameter to define the efficiency. Okay, so generally manufacturer mention this fill factor on the label of cartoon of the solar cell and many in the brochures also. So these are technical requirements that has to be fulfilled by the solar cell manufacturer. So what I will do, I will leave you guys with this slide for 2-3 minutes, so you guys can have a good sense, a fair idea of what a fill factor is. Okay. And if there are any query regarding this, you can ask also in between. Okay, so no question. So let me move to the next slide. Was- So yeah, this is basically what I will say is yeah, I think I can. So this is the electrical circuit. You have to identify what ABCD is, and these ABCD symbol and components are mentioned here. So you have to match this symbol with the component. Okay, so it's very important you know the how to identify the devices in the circuit, because solar cell is not only a solar cell, it is basically combination of different circuits also, it can be said. So if you have to obtain a power, the solar cell are actually connected in a module. Cells are actually intermingled in a module. Okay, so basically what I will say, so A is basically, if you see A, so what is this? So I think most of you will identify if somebody not from science background. So this is a symbol of ammeter. Okay, it's showing current. So what it will see, it will show the photocurrent. What is photocurrent? Current generated from the light. So correct option of A is 4. This is correct. And for B, what is B? So B is basically, you see that B is parallel to D, and it is also parallel to C also. So B is basically shunt resistor due to internal combination of electron hole pairs. So it's basically a shunt resistor. Okay, B. C is C. So when we see C, it can be series resistor also, like C connected in series to D. And it can be load resistor also, depending on the different circumstances how you are using C. Okay. So it can be, if it is load resistor, D will be series resistor. If it is series resistor, D will be load resistor. Okay. So depending on that, option, these two will be common and these two will vary depending on how you treat C. So if C is load resistor, D will be series resistor. If C is series resistor, D will be load resistor. Okay. So option A and C both are correct. I will try to focus on this circuit. I will erase the marks here so you guys can easily understand it, and try to focus on this circuit. How, and this is diode basically. This is diode. And what is the function of diode? I will not explain it now because I will uh, take this as a homework. What is the function of a diode? In next live session, I will ask you guys. Okay. Okay, so if there are no queries, shall I move to next slide? Okay, so next slide is basically asking about open circuit voltage. So open circuit voltage of a solar cell is what? Vary linearly with temperature. This is correct option. Varies with logarithm of photocurrent. So as of now, this is basically a conceptual question which you can grab from concept. I can discuss the whole maths behind it, but as of now you can understand that it varies linearly with temperature. As you increase the temperature, the open circuit voltage will increase. Similarly, with decrease in temperature, it will decrease. But with in case of photocurrent, it takes a logarithm of the photocurrent. Okay. So that's how it varies. It's very not exponential. It's logarithm of photocurrent. It does not vary. This is a wrong statement. Okay. So I think it's basically only a conceptual question. Bulk lead sulfide material can absorb the full visible spectrum because when can a material absorb the full visible spectrum? Full visible spectrum. For visible spectrum, you remember 400 nm to 700. Is it so or something? 400 to 700 I remember. Otherwise, if there are some other values, you can let me in the comments. So yeah, full visible. So it must have a pretty good band lab. Uh, the band gap must be actually so much that it can correspond to such a longer wavelength. Okay, so because 400 to 700 is a longer wavelength, 300 nm. So Berkeley subside band gap corresponds to a longer wavelength that can corresponding to this region. Okay, so it has a longer wavelength. You remember this band gap thing. So this conduction, this is valence band. If this is 300 nm of wavelength, it will absorb the light. Okay, and the electron will jump from it. So it is a direct band semiconductor, direct band semiconductor. Correct. Berkeley lies in the middle of this region. So if it lies middle of this region, then it won't absorb all the full visible spectrum. It will absorb only half or maybe three-fourths of this spectrum. Okay, so it corresponds to longer wavelength. So this is the correct answer. Okay, what I will do, I let me put this right for a few minutes. So you guys, if you have any queries, let me check the chat box also if somebody has posted any queries. Okay, no queries. I will put this slide for a few 1 minute or so that you, if you guys have any queries, you can ask. Okay, so let's move to the next question. Dash solar cell improves solar cell efficiency by using materials with dash band gap values. Okay, so the correct answer is tandem solar cell improves the solar cell efficiency by using materials with different band gap values. So one thing is that if materials with different band gap values can be used, so it will absorb more kind of light. Okay, and the tandem solar cell is basically a stacks of p-n junction. So each of these is actually formed with different band gap energy. So it will actually helps in absorbing a long range of spectra, not like amorphous silicon or something. Okay. So basically, tandem solar cell improves the solar cell efficiency by using materials with different band gap values. So correct answer is this: a tandem and different. Okay, so correct answer is option B. Okay, so if there are any questions, you can ask them. Okay, so no queries. Let's move to the next question. It is basically a conceptual question where you have to apply formula kind of thing. So you just have to remember the formula. So these values can be changed and can be asked in the NPTEL final exam also. So make sure these type of whenever these type of question are asked, you don't get it wrong. Okay. So these are very easy questions. If the refractive index of glass and air is 1.5 and 1 respectively, then what should be the ideal refractive index of the anti-reflective coating material? So the correct answer is 1.225. And how it is obtained? So I put a next slide also here. So basically, the anti-reflective refractive index of anti-reflective coating here is square root of refractive index of air into refractive index of that glass or that material or anything. Okay, these are multiplied and a square root is taken. Okay, it's basically a geometric mean, you can say. So for glass it was said that it's 1.5, for air it is 1.0. Okay, so you put 1.5 here, 1.0 here, 1.0 into 1.5, 1.5. So the correct answer comes out to be 1.225. If I change the value of n0 to 1.5 or 2, okay, and change the value of ns to 4. So what should be the refractive index of anti-refractive coating now? So just simple put n1 equal to 2 into 4 equal to under root 16 equal to 4. So this would be the refractive index. Okay. It's generally high refractiveness, but for this type of question, okay, so this type of question can be solved like this. So yeah, if there are, I will put you guys to this slide for 1 or 2 minutes. So if there are any queries, you can ask. Okay. Okay. So no questions. Let's move to the last question now. Okay. So yeah. According to Shockley-Queisser limit for the single p-n junction in dash AM basically air mass of 5, solar radiation, band gap of 1.34 dash percentage efficiency is obtained. Okay, so if we see the correct all of the options, basically in concentrated we can obtain the more higher efficiency than 33.4. Okay, so it is basically unconcentrated. Air mass 1.5, solar consumption with band gap 1.4, 33.4% of efficiency can be obtained. Okay, so the correct answer is this one. So the correct answer is A, unconcentrated and 33%. Okay, so I think with this, all the question we have discussed from non-graded part of the assignment and graded part of the assignment. So I'm sure that you guys must have got a good, pretty fair sense of idea about how to approach solve this question. And this whole session is actually video recorded on, and the recording will be uploaded on YouTube. And the links are also shared in the problem cell. When you open the NPTEL, there will be a tab called problem solving session where you will get these links, weekly links. So for week 6, you will get the link for YouTube, and you can access this live session. If you have missed the live session, you can access the live session through YouTube. You can see it from there also. Okay, so that is the main concept here. Okay, so anybody who have missed the class can see the live session from YouTube also. So I will request you guys to go to YouTube, and if there are any question, you can ask in the comments there also. And if I will suggest you guys to ask in the discussion forum so that everybody can benefit from your question. Okay. So yeah, thank you, and all your queries are welcome. I'm sure that you have enjoyed this live session because I've discussed the concepts, important concepts here, discussed graded assignments and different questions. Somebody wants to join at 9. Okay, let me see if wants to join at 9 a.m. It's 9 p.m. It's okay. So yeah, it was a very good session. I'm sure you guys have got a pretty fair sense of idea. If there are any questions you want me to address, so you can always find me at this email ID. Okay. So okay, thank you guys for this session. I'm ending this session now.
So if you have any questions, you can ask, or should I end this session? Questions now? Okay. Okay, thank you guys.